Hi, all, this is Mr. Yeager for chemistry, and we are looking at equilibrium. All right, this is very much going to be a conceptually qualitative analysis of equilibrium. We don't get into calculations so much in on-level chemistry, but there's still a bit to go through, and we need to make sure we understand the factors that can affect the equilibrium of the reaction. We'll get into what that really means and go from there with it. So again, another excellent presentation made by another chemistry teacher that I'm using to make the video. So here we go. All right. So we have always said reactions basically go one direction. Okay. We have said that, you know, the reactions go from reactants to products, and that's the way it goes, and then it completely is done. What is really true is a lot of reactions, like that second bullet point says, don't go all the way to completion. They don't all just completely become products. All right. What some of them do is they get to a point where they create a lot of products, but then there's too much product, and so those products actually react back and turn back into the reactants. So we say that reactions can be reversible. Okay. This is not the best example, but I mean, think about the idea of recharging a battery. The whole idea of recharging a battery is you're reversing the direction that the chemical reaction is occurring in that battery, so that you are recreating the original product, or sorry, reactants that then can then produce that electricity well again. But you're going to have to provide some sort of impetus and some sort of force to make that go in the opposite direction. Now, what we're saying here is you don't need to always provide that additional force to make it go back in the opposite direction. Some reactions just do it on their own. All right? So a reversible reaction is exactly as it sounds. It's a reaction that can go both directions. Reactants make products, products make reactants. We then draw the arrows down here going both directions. We still say the reactants are on the left and products are on the right, but we do say the reaction is going both ways. All right, so the forward reaction, I'm kind of just going through some of these terms, is exactly as it sounds, is obviously the reaction, the side where we're going reactants to products. That's what we've always referred to as any chemical reaction, is the forward reaction. The backward reaction, well, I guess that's the next one. The reverse reaction or backward reaction is obviously where you're going from products back to reactants. Pretty straightforward there. Okay. Equilibrium is when you have a reversible reaction and it has reached a point where both reactions are occurring at the same time and at the same rate. In other words, whenever you have a reactant becoming a product, at the exact same time you have a product turning back into the reactant. What that means is there will be no overall change in the amounts of the substances, because anything that's going forward, there's some part somewhere else in the reaction that's going backwards. So basically the concentration of the substances become constant. It doesn't mean that they're equal. I think that's the biggest thing we make mistakes on. In honors chemistry, we start doing actual calculations and everybody goes, oh, they're just equal to each other. Nowhere are we saying that at equilibrium do you have equal amounts of products and reactions, or products and reactants. I completely understand why people see that, because they're like, it's in equilibrium, that means things are equal. No, 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 no. Equilibrium just means the rate at which the reactions occurring are the same. It doesn't mean the products and reactants are equal to each other. But the overall amount of substances no longer change. All right? So there are important things to understand about this, okay? There are conditions, as it says there, that we need to have in order for equilibrium to occur. It needs to be what we say a closed system. So in other words, nothing can leave the reaction, okay? You can't pull out any of the products. You can't remove any of the reactants. They can't escape, okay? The temperature must remain the same. We're going to see temperature is one of those, I'm going to quote unquote say forces. It's not a force because I teach physics. It's not a force. All right. But one of those actions, one of those triggers that can make the reaction move left or right or left depending on what the temperature is. So we have to keep that constant. And then we have to allow the reactants and products to continue to obviously go back and forth. We can't try to stop one side of the reaction. All right, so this is a good kind of little like picture simulation of it. Obviously, if you only have reactants, you're going to have the forward reaction only. But once you start creating some products, the reverse reaction does begin. But you can see based on the arrows, this reaction still wants to go really, really forward. It'll start coming back a little bit because we have some of the products. And what you'll see that bottom arrow start growing as we start going farther, and the top arrow shrinks. So it starts moving and moving and moving, okay, until there's a point where the rates are equal, okay? So going back again. So when we only have reactants, obviously the only way for it to go is forward, and the reaction will continue to more dominantly be the forward reaction through much of this until you reach a certain point and a certain amount of products and a certain amount of reactants that the rates are now equal. You could see the amounts of reactants and products are not equal. We are now saying the rates are equal. So as the reactants continue to form products, the products do just enough to make those reactants again, and therefore the reactions are at equal rates. Okay? That is equilibrium. All right? So like if I kept on trying to like hit the forward arrow, we would see these amounts stay the same, and it would just continue to be that way unless there's some outside trigger. Okay? So equilibrium reactions are written the same way as chemical reactions, chemical equations. We have reactants on the left, products on the right, and like I said, we just do a double-headed arrow. All right? With graphs of these, graphs of equilibrium reactions, what we see a lot of times is we see, like this first graph is very similar to the simulation. We started with all reactants and no products. Initially, it was going very, very, very quickly, and then over time, that forward reaction was going very fast, and a lot of products were being made, and then over time it slowed down, and then when you hit equilibrium, the reaction continues to go, but the amount of reactants and the amount of products don't change. This is another example where the reaction goes, but you can see we didn't have to make nearly as many products to be equilibrium, and then they are staying the same the rest of the way. The big thing is they just don't have to be equal. The amount of reactants and products, the concentration does not have to be equal. They just have to reach a point where they produce each other at the same rate. All right? Actual applications, okay? When we produce different chemicals, when we produce different products, we always are trying to develop some sort of equilibrium process that we allow the process to get to equilibrium, but what we will do, and you'll see in a moment, is we're going to manipulate that reaction where we then pull that stuff out, and then we'll keep on having the reaction continue to go through, okay? The movement of oxygen through your blood is very important, obviously, to make sure that, in this example, you are treating altitude sickness. It also maintains blood pH. Baking soda and refrigerators remove odors. Carbon dioxide in Earth's atmosphere and oceans. Obviously, there's a certain amount that goes in the atmosphere and a certain amount in the oceans. I mean, that's all at equilibrium. So that leads us to the very, very, very important LeChatelier's principle. Okay? LeChatelier, that's how you say it, LeChatelier. All right? This principle is stating how you can manipulate the equilibrium, how you can shift the equilibrium toward the products or toward the reactants. All right? So this occurs, as it states, if there's some sort of change in the system that's already at equilibrium. So it's already at equilibrium, and then you do something to it to make it shift, to make it go, whoop, we're not at equilibrium anymore, let me shift one way to the other, or find the new equilibrium with something like temperature, okay? So, if we say the system shifts toward the right, we're going to say we want more products to be made. If we say the system shifts to the left, we want more reactants to be made. What we are looking for on these problems in a moment, and we're going to do a lot of examples, is we need to see which side is the stress. We're going to call it a stress. We're going to stress the reaction on one side, and then that side needs to relieve that stress by shifting the reaction to the other side. That's what we're looking at here. So, examples of stresses, or I've been saying triggers, but we're going to use the word stresses now, are concentration, we're going to add or remove substances, temperature, and then pressure or volume. Pressure or volume only affects gases though, okay? And pressure and volume are inversely related. Concentration, as we already know, is measured in molarity, and we would be where, so here's the key, here's the stress. If we add a substance, whichever side that we're adding that substance, the reaction wants to shift away from that addition, because what we're doing is it's at equilibrium and then we're stuffing more in on that side. So the reaction wants to move away. So when I add, it'll always shift to the opposite side. Vice versa, if I remove that substance when it's at equilibrium, it's going to shift toward that side. So you can see how that works in manufacturing, because it'll create, like you have a reaction, it creates product, product, product. It eventually reaches an equilibrium point. Well, if I pull all that product out, what's the reaction going to do? It's going to be like, oh, I need to produce more product. So that's what we do in manufacturing, is we keep on manipulating the equilibrium to make sure that it keeps on shifting to the direction we want it to, so that it creates more products. Okay? Now, again, if I add, it shifts to the other side. If I reduce, it shifts toward the side that I reduced. All right? So here's the things. If I add a reactant, it's going to move toward the product. If I remove a reactant, it's going to move toward the reactant. If I add a product, it's going to move toward the reactant. If I remove a product, it's going to form more product. That can be a little confusing just listening to it, but just pay attention to the chart. Heat, temperature. This is where we have to pay attention to where it's an endothermic or exothermic reaction. Again, endothermic means you're absorbing heat. Exothermic means you're releasing heat. What you will see on this, okay, is we will add heat as a quote-unquote product or reactant in the problem, okay? So if it's an endothermic reaction, heat is on the reactant side. If it's an exothermic reaction, heat is something that's being produced. It's on the product side. We can then treat heat just like concentration, where if I add heat to the endothermic reaction, we don't want that, and it's going to go to the other side. If I remove heat, it wants more heat, then it's going to move toward the reactant side. So heat we can treat just like concentration, where if you add it, it moves away. If you cool it, it moves toward it. So that's what this is saying as well. All right? There's just the example again. Now, one other thing I want to point with this is if they don't have the word heat, if I give you the delta H and I say the delta H is positive, that means it's endothermic, and therefore if I add heat, or if you see it's positive H+, you add heat to the reactant side. If you see a negative enthalpy, you add heat to the product side. So that's another way to make sure you recognize what might happen with this. The last one is pressure. All right, now this is only if there's gases present. Okay, so only if you see gases, and we're gonna write out in some of the reactions, we're gonna write their states of matter. So you're gonna have to pay attention to that little parentheses state of matter, S, L, G, or AQ. You only care if it says G, okay? So we will have that, okay? We will have to use, we will have to count out the coefficients to see the number of moles of gas, because maybe I have a reaction where it's all gases. You need to see which side has more gases based on counting up the coefficients. So we'll see if we get some examples of that. If I increase pressure, I'm going to move toward the side with less gas, okay? Because gas needs a lot of space. So if I increase pressure, I'm pushing that gas together. It doesn't have enough space to keep on being present, so it needs to move to the side of less gas. If you decrease pressure, you shift to the side with more gas. If equal amounts of gas is present on products and reactants, it's not going to change at all, which we might ask you that. That's always an interesting one to see students figure out. All right? So, let's do some examples with that, and then we are done. So there's a couple examples on each of these. All right, so we're going to see which way it moves. Okay? Go back. All right, so right here. I'm going to change the white. I have my reaction here. All right, this has all sorts of stuff to check out. First off, you see PCl5, here's my reactants, here's my products. You can see they're all gases, so pressure will have an effect on it. It's already balanced, we will give you these already balanced. Okay, we're not going to make you do that. It gives you the delta H is positive 87.9, which means this is endothermic, which means heat is on the reactant side. Okay, so all we're asking is, will it shift toward reactants or will it shift toward products based on these different pressures, these different stresses? I'm removing Cl2, so if I take Cl2 out, this reaction needs to make up for that loss. So if I remove Cl2, this is going to move toward products because I need to replace it. All right, temperature is decreased. If I decrease temperature, basically just the same thing I just did with the Cl2, I'm decreasing the heat. I need to replace that. That's going to go toward the reactants. Pressure is decreased. Pressure is decreased. Everything is a gas here, so I need to count out which side has, how many gas molecules I have on both sides. On the reactant side, I only have one gas molecule because it's only one coefficient. On the other side, I have two gases. So if I decrease pressure, that favors more gas. So that will favor the product side. And then I add PCl3. If I add PCl3, I'm adding more on this side. I want to get rid of that. It's going to push to the left. That would move toward the reactant side. Okay? So I mean, you got it. It's a lot to remember, all the different stresses, but we get the same idea, other than pressure kind of, with the idea of concentration and temperature. All right. All right, so this one you got very clearly heat is on the reactant side, so this is endothermic. Again, a lot of gases, everything is balanced. Let's go, okay? Decrease the concentration of H2S. So I'm pulling H2S out, so I need to replace that, so that's going to move toward the reactants. Okay? Increase pressure, so I need to add up. I have 3 gases on the reactant side. I have 5 gases on the product side. If I increase pressure, that supports, I want less gas. So that's going to support the reactants as well. All right. I'm going to now increase the temperature. So I'm adding heat. I don't want all that, so that's going to shift to the right. So that would be products. Okay. Increase concentration of CS2. So I'm adding more CS2, I don't want it, move to the other side. So that's back to reactants again. And then it says take out CH4, decrease CH4, so I need to replace that. That's also toward the reactants. So most of these supported moving the equilibrium toward the reactants. One more. I have 5CO. So this one now I have some gases and solids, so that's kind of good to see. And I finally have heat on my product side, so this is an exothermic reaction. All right, so it's decrease pressure. All right, so I need to count out all gases. I only have 5 here. Wow, this is a lot. So I have 5 gas on the left side. The I2O5 solid does not count. So I have 5 gas on the left side. I have 6 gas on the right-hand side, so barely. I'm decreasing pressure. That supports more gas, so that's going to be products. All right. All right, raise temperature. Raise temperature, so that's going to add more heat. I don't want that. It's going to move to the other side. That's reactants. Add CO. I don't want that. Move toward products. Add CO2, it doesn't want it anymore, move toward reactants. Remove I2, so I'm taking this out, I need to replace it, so I'm going to move toward the products there. So that's basically it. I mean, there's obviously plenty more examples to play around with, okay, and for you to go through, but that is the using LeChatelier's principle, all the different concepts for equilibrium to get. And that's all.